Organization. Okay, so you will have free lunch, but there's nothing like good lunch. Somebody will pay, but somebody will pay. So in order to collect the money from the person to pay the lunch, 10 people, 10 elected people from you should sign the rest.
Not from ICT.
Not people from IFT, but because this is like money. So people from outside the IFT, preferentially professor because they get more money, and then we go down. For docs, for students, but I mean, you sign it, you receive money, but you won't receive money to pay lunch. Okay.
You're doing pro bono work.
Exactly. Okay, this is one organizational thing. The other organizational thing is that we will better this currently. So there will be one more before the end of the semester, and then next semester will be 3 or 4, and hopefully this to take off and we have it speak forever. And the other thing is that please get involved in the organization, so we just keep it on, but we don't want to get it off all the time. So the idea is that you suggest speakers, which you can suggest yourself as a speaker, suggest large speakers, provided they are free, of course. And so we are open, we don't have any slot for next speaking, and we don't have a fixed date for next speaking, but it will be sometime in the day. Okay, so maybe before we start with the first talk, we go just go around, everybody says 10 seconds, 30 seconds who he is, she is, I mean, what is the level, professor, master, student, whatever, and very broadly, what is the area of interest. Let's start from here.
Hello everyone, I am Louis Legrand, a postdoc at CTP, and I work on the CMB computational lensing, and also on the correlation of the CMB with galaxy service.
Hello everyone, I'm Isabel. I'm a postdoc at IFT. I work with Legrand. I do gravitational wave cosmology. Technology with gravitational waves, especially gravitational.
Okay, so I'm Walter Gilbert. I'm a new postdoc here in the ICTP, and I work mostly for galaxy surveys, in particular the Activity Survey and LSST right now. And my main interest is trying to look for remote velocities in the galaxy.
Right, so who's undergrad student? We're going to show how long.
You are hosting,
From
you are on cosmology.
yeah, I'm studying cosmology.
First, when did part in my master is which work with Mach simulations.
Got it.
Yeah.
From Paulo, and work with multi-tracer and large scale structure.
So PhD students and Professor Paulo and I work with students.
So hi everyone, my name is Natalie. I'm a final month PhD student. So mostly I try to do cosmological parameter wave inference using machine learning and a bit of halo galaxy connection, working with Paulo, and I think that's it. Yes, I am Natalia, a PhD student, also a whole student at the University of São Paulo. And I work with machine structure and applications of machine learning cosmology, like Quasar classification, halo galaxy connection.
Nicholas, I'm a PhD student at the Federal University of Alicea under Professor Andrea Lufu. I work with quantum theory of spacetimes and in particular holography in non-NDS spacetimes.
Hello everyone, my name is Jose, I'm from Peru. I am a master student and I do my master program in Mackenzie Presbyterian University. So I'm in another research field. To me, it's very interesting. I'm working about the effects that space weather in the lower ionosphere.
So hi, my name is Ron. I'm a PhD student in IFT, UNES. I work with Rogério, and my work is about observational cosmology, more specifically analyzing non-standard dark energy models to solve cosmological tensions and anyway, just explore games.
Hello everyone, my name is Isabel. I'm from USP.
and I just finished my master's and starting the PhD right now. And I work with scaling relations in galaxy clusters.
Hello, I'm Lucas. I'm an exchange student, master's level, working with Raoul from the Uppsala University in Sweden. Currently doing a very small project about quasars in the Gaia survey.
Hello everyone, my name is Rodrigo. I'm a postdoc in the IPC in Spain, and I work mostly with theoretical cosmology and simulations.
Don't say anything.
Okay, so I think we can start. I mean, you already introduced yourself, so it's very convenient that you were the last. So,
So you also introduced a student here.
Yeah,
Is visiting for,
no, yes.
Yeah.
I worked with Marcus Miller. I did my master and PhD with Marcus. First question. Anyone knows how to put full screen here? You can figure out? No, I can. I don't find it. Yeah, please.
okay. There is a link comment. We will introduce ourselves. So,
yes,
Hi everyone, my name is Gabriel. I'm a master student at IFT.
ah,
I'm working on Recap. So,
yeah, Gabriel, please go ahead.
yes, my name is Gabriel. I'm a master student at IFT and I'm working on Recap. I'm studying gravitational waves. That's it.
We will chat to each other.
Hi, my name is Laert and from Yazoo.
One more.
Like, with us, I mean, as well.
so we just all introduce ourselves. You're the last one, so.
Okay, my name is Leonardo. I'm from the University of São Paulo. I am a PhD, I'm PhD student. And I'm here to see what's going on with physics in Astro. And I work with lensing.
Awesome. The number stabilized. Okay, so let's say 45-ish plus 20. Yeah.
Okay, yeah. Please feel free to escape. Try to take time. That's more informal. So, okay, yeah. Today my idea is to talk about different subject. So I completely changed the title and my presentation for today. Sorry, because I think that most of you were in the EFT the last week. So today I need to talk about how to use continuous normalizing tools for simulation-based inference, particularly in cosmology, of course. So the idea is to be more introduction to the subject. So I start to introduction to simulation-based inference in general. Then I need to move to introduction to continuous normalizing flows. I don't know how familiar with this subject. Then I go into application of the continuous normalizing flows to the simple case of a Gaussian based field. And the last thought is about how to put something more realistic, like Galaxy or actually any tracer, and how to run all the pipeline with some tracer. Yeah, right. So let's start with the basics of inference. So the whole idea of any inference is to compute the posterior PDF, which gives the probability density of some parameter, giving some observed data and some model, right? So we want to get this guy here, and because of the bias theorem, we know that we can get this PDF from the likelihood times the prior, times the normalization. I will not talk about here. But we can also Yeah, so the posterior from the joint distribution, which is usually not used in cosmology, but we will see that with the simulation-based inference, we can actually compute the joint distribution. Okay. So these are all elements in the usual inference. And for this talk, the most important ones will be the joint, the posterior, and the likelihood. Okay. The prior will be it's very important, but will be the same of the usual experience. And the Bayesian evidence is also very important if you want to compare models. But here I'm not going to talk about this. So because of the bias theorem, as I said, we can just assume a likelihood and use this likelihood to get the posterior using, for example, a CFC. So for the likelihood, we have to basically have three main elements here. The first one is the likelihood itself. We have to assume something for this likelihood. The most usual function that we assume is a Gaussian. This is because of the synchrony limit theorem. Okay, so we don't really know the likelihood of the observations, but in the assumption that we have many different realizations that we are taking the average, we can just take a Gaussian. The second thing that we need is some model for the observed data given a parameter and the underlying model. Okay. For this, we can take either a theoretical model, like I don't know, like 10 or something like this, or you can use emulators from simulations. For example, HaloFit for the nonlinear matter power spectrum. Okay. And the last component is the inverse covariance that we also need here. It's also a function of the parameters and of the underlying model. And for this, we usually use some fast simulation, for example, like sales, compute this covariance for some observable. Okay, so we need these three main elements here, and the likelihood is usually the main component of the inference. Okay, but if you think better about the likelihood, we see that the likelihood is the same thing of our simulator, right? Because the simulator is just something that you put some parameter and some modeling and get some realization of the data. For example, we have any more simulations. It's just a likelihood, okay? It's just an implicit likelihood. Because you put your cosmological parameters, you're modeling like the Newton gravity and get the final density grid, and you can also, I don't know, measure spectra, measure the bispectra, and measure anything that you want, and get some realizations that have some scatter. Okay, so it's the same thing of the likelihood. And you can also see that the other two components of the likelihood here, the model and the covariance, you can also get from the simulator, which is the likelihood. It's just the expectation value of some measurement, which is some data. So the point here is that the simulator is everything that you will need for to run an inference. Okay. So going back to the Bayes theorem, so the idea of the simulation-based inference is to try to emulate using neural networks usually some of the three PDFs here. Okay. The first thing that you can do is to emulate the joint distribution. So you want to model the PDF of the pair of parameters and data. Okay. And at the end of the day, you want to take a slice when the data is equal to your observed data. But the problem here is that you have a high dimensional PDF because you have the combination of the dimension of the parameters and data. And also you have to take this slice usually in a high dimensional space. One way to do it is, for example, using the ABC, which is the approximated bias computation, Bayesian computation. But it's very hard and usually it's not feasible high dimensions. The second way to do it is to directly emulate the posterior. This is very good because it's the sequence that we want to get in the end. But the main problem here is that you are restricted to your prior that you have used it to generate your simulations. Okay. And the last thing that we can emulate is directly the likelihood. And this is good because we are independent of the prior, in this case, but we have to run some CMC to get the posterior as we did here in usual analysis. Okay, so those are the three main ways to get to the posterior using simulation-based inference and specialist neural network. Of course, you can use some other methods like ADC, that where you don't need neural networks. But neural networks, I think that's the standard now.
So, Rodrigo,
Yes.
your last point. I'm not sure that this is true because the prior is implicit in the simulation.
Yes, if you are trying to, for example, to fit
But
for
I mean the last. You said that this method is independent, right?
yes.
Actually, it is not, because if you are using the simulation that it right. That's my point.
It's independent in the sense that in the end of the day, you put it, you change the prior. The prior here is so important for you to get a good resolution in the regions that you want, right? To get a good fit of this expression as function of theta in the region that you really want the parameter, right? But we should completely change the prior that you have used it to generate this relation. But it's not the case for the joint for the posterior. For both cases here, you cannot change the prior that you have used it to generate the relation. Right? That's the point. That's it. Okay, so I hope I convinced you to do why to do simulation-based inference. Basically, the main point is that all information that we know is in the simulator. Okay, there's no reason to not use just the simulator, and no reason to not use all the information in the simulator. Okay, because usually we don't know the likelihood of the problem. Even for the power spec, we don't know the likelihood of the power spec, right? We usually just assume a Gaussian, but we know that's wrong. Okay, especially for low K, we know that's not a Gaussian and might have some problems. For example, when you fit, I don't know, things that are important in large scales, for instance, okay. So it's important that the likelihood is not Gaussian, even for the power spec. The second point is that the likelihood is also very expensive to compute, actually, right? If you think that you have to compute something like the model and the covariance for each parameter, it's very, very expensive if you want to compute it properly. So it's not really that you are not really saving time using some likelihood. The fourth point is that the likelihood, if you want to do something like AMCMC, you have to compute the likelihood on the fly, right? Because to move in the parameter space, you will need to know your current position in the parameter space. That's the deploying of Monte Carlo Markov chain, right? And with simulation-based inference, you can just run many simulations and use this data to train your PDFs. So it's better to handle this data. And the last point that usually with our simulation, we don't use all information that we have in this simulation, right? We usually just use the mean value and the covariance, basically to compute the D and C here, right? So, and again, we know that the data probably has more correlator, more adequate functions, right? About the covariance of the mean. Okay, so any questions so far?
So I think I'm still a little confused of how do you use your simulation practice, right? So it's not, you will not compute any summary statistic nor anything, right?
Oh, you can. You compute. Yeah. The simulator here, you can think like, for example, in cosmology,
Yeah.
you could think like the N-bar simulation plus some lifecon plus some estimation of CLs.
Yeah.
So the CLs would be the D, right?
Yes.
And the simulator is the whole process, not just the N-bar simulation, but also the process of measuring your particular summary symptoms.
So the thing is that I don't see the difference on computing just 1,000 simulations, measure the CLs for each of them, and then you use like usual likelihood, right? I don't see what's the difference now. I'm really confused. Sorry.
Okay, yeah. I think that the main difference here is that the usual likelihood,
Yes.
you have to assume a likelihood, right?
Oh,
In the simulation, you have at least likelihood that it's more reliable, right? Than
Okay.
like Gaussian.
But you will still compute summary in practice. You will still compute summaries that exist over the simulations.
Yes.
Okay.
Yes. In next slide, I will show that you can actually use the whole density field. Well,
Okay.
Yeah, I think I had kind of the same question. At the end, in order to evaluate, I mean, suppose that you have a well-behaved probability that has a minimum, a maximum, sorry, right? So in order to evaluate the uncertainty of that estimation for whatever model parameters, you need some metric in that whatever space that you have there. That metric is in some sense, you have to choose that. You can choose to be whatever you want, but you need a metric. Otherwise, you don't know how well you're fitting and how bad you are as you move away from that best fit. So when you do that, you have to assume some metric, and God knows what could be something which amounts to be just the Euclidean metric, which is what you call a likelihood, right? So how is it that you're not trading 6 for half a dozen when you're doing this?
okay, yeah, the point is that the metric here is very natural. By metric, I'm saying that I want my PDF and these three guys to be equal to the true PDF. That's my metric.
Good.
Yeah, the point is that I don't know my true metric, my true PDF. Yeah, but I sampled for my true PDF, right?
Sorry, no, I don't follow. What is it? How do you get a true PDF if you, like in principle, if you, unless you're imposing some prior on models and parameters that tell you that, this is what the matrix is beforehand. How do you know that? If, sorry.
Yeah, I think that I'm going to go back to this point. So in maybe 3 or 4 slides, so we can come back to this discussion. But yeah, that's a very important point. Okay, so yeah, so now let's move on to the continuous normalizing flows. And okay, we decided that we want to do simulation-based inference, but how to do it? And with neural networks, we should use. So why to use continuous normalizing flows? Okay, first of all, why to use neural networks? Because we know that neural networks are universal interpolators, so I don't have to assume any shape about the PDF. So it's very nice, right? And we had a lot of models for neural networks. The second point is why to use this specific category of neural networks, which are the generative models, okay? And the point is that we only have samples of the likelihood, okay? We don't have the actual value of the likelihood. So we are not trying to interpolate the likelihood like we're doing a usual interpolator, like for the power spectrum, like Hill. We have the value of the power spectrum for HK, and we interpolate this. Here, we basically just have the case, right? That follows the distribution of the power spectrum, this looks like this. So for this, we have to use generative models. And explain more of these 3 last points here. And one choose specific normalizing flows, which is a class, which is a model inside the generative models, is mainly because normalizing flows can get the explicit values of the PDF, which is very useful, especially if you want to emulate the likelihood and use it to run a CMC. And also normalizing flows have a great occurrence for the PDF to describe the PDF with the line. And the last point, why is you use this continuous normalizing flows, which is a improvement of the standard normalizing flows, which is, I show that it is mainly because it is more expressive than the usual normalizing flows, because the usual normalizing flows have put many constraints in the architecture of your neural network. Okay. So let me talk about the generative models. What's the idea of generative models? Is that we only have a set of some variables, some parameters, something, and that were generated from through PDF, and we want to recover the true PDF. Okay, but we don't know the value, for example, the value of the PDF for each value of the variable. We only have a set of variables. So the idea of this kind of models is to try to, or implicitly, either explicitly, get the PDF. So if you have the PDF, we can just generate new samples from this PDF. One very famous example is in the image generators. For example, the DALI, which is a diffusion model, which is a class of generative models. We can just start from some latent space, which is just white noise, in this case here, just Gaussian noise, and applying the technique, get some images. Okay, so we know that for images, this class of models very powerful, and the idea is to apply something similar for simulation-based inference because we have basically the same problem. So I think that here I can explain the questions that we had. So what's the point in cosmology? Okay, so first of all, we have to sample parameters from a given private. Okay, if we have to know this private, have some idea what are the good parameters that we want to look at. Then, given the parameters, we run our simulation, which is just our implicit likelihood, okay, which is the same thing. Here with sync, but it's the same of like the previous slides. So in the end, we have a set with the parameters and the data, which might be, for example, the color spectrums, the CLs, or anything. Okay, so with this set of parameters, we run the neural network to implicitly learn one of the PDFs. Okay, and with one of the PDFs is anything that we want. I don't know if it explains or not. And here is the point that how we compute what's the method, what's the loss function. Okay, it's just the difference between the chiral divergence between the true PDF and the PDF given by the neural network. But because we have sample from the true PDF, we don't need to know the true PDF. It's the same technique that we use in, for example, in MCMC, right? Because we are making the average over the sample data from the PDF. So the PDF, the true PDF is implicitly given. So we don't need to really know the values of the PDF. So the loss function is just the log of the likelihood predicted by the model, which is proportional to the chiral divergence, the true yes.
So this is like normalizing flow that you have, two distributions of two different things, and you map between them, and there's a mapping internally, which is whatever nonlinear. It doesn't have to be Gaussian, and this is what you're calling the distribution, that way that you can go from data to parameters and back. So your P of the parameters, in some sense, as you map from the data to the parameters, you learn that mapping. That's what you say. That's what you mean by there's no intrinsic putting by hand. You're just assuming that the code that the machine learning behind it learns this mapping.
Sure, it's
well, you have used a certain.
The PDF is the PDF. The transformation is the transformation. Separate.
Yeah, but then what is the PDF in that sense? I mean, you have chosen a certain set of parameters, which is your initial parameters, right? And you just produce simulations on that, right? So you have a kind of a many realizations with many different values of the parameter. Then you have your data. Then you ask, what is the likelihood of the parameters or the probability for the parameters for a given set of data? Right, so you have to know how to map that point back to a kind of a cloud here in parameter space. This is what normalizing flows, for instance, does, right? So that mapping is the probability of the parameters giving that data. Yeah, so this is what you mean that this mapping, you're assuming that the code knows how to do it, it doesn't assume anything. That's
Yes.
all right.
Okay, let me just talk about the loss function here. This is just the chiral divergence. So we have the chiral divergence between the neural network PDF, which is a function of the parameters of the neural network, and here we have the true PDF. Okay, let's say for some variable x.
Sorry, there you go. So, yeah, I think I'm still confused what do you mean by PDF here in this context? How do you obtain the PDF from simulation, from one person?
From simulation.
See,
Yeah, you take the parameters from the prior,
yes,
okay?
yes,
Then you take the data from the lighting, which is the simulation itself.
yes. A three-dimensional simulation from,
Yeah, anything, any kind of simulation. You want.
okay,
For example, a bar simulation.
like on paper. Okay,
Yeah, so now you have this pair of parameters and data.
yes,
So from this, you can get a lot of parameters and data, okay? Let's say n of this. Okay, you run the simulation many times.
yes,
So you have many pairs of parameter data.
okay,
And with this, you have basically sample from the joint version of parameter data, right? The true joint.
Simulation.
Yes, I assume that my simulation is the truth.
right,
Good. So here I have sample from the true joint. That's the idea. So I know because of the points that I have here, I have some information about this distribution. Okay, so the idea is to compare the distribution given by the neural network with the true one. This is just, we just take the chiral divergence, compare two functions, and the string given, because we only have n. Yeah, this is basically something like the true distribution times the log of the neural network minus the log of the two. And of course, here is the function. Right. This guy here is not important because it's not a function of theta, so the correct is 0. And this thing here is just the expectation value of the log. Where I took this expectation value with respect to the true posterior, right? So my loss function is just the expectation value of the log of my predicted PDF.
So I understand the right hand side, but can you see this telling what the loss function set for the left side? I'm glad. I mean, you are getting the loss function to the PDF. But so what does the loss function represent?
Represent the difference between the two PDFs.
The mean sort of mismatch between
Yes.
the modeling and the
If the two PDFs are the same, this is the one.
okay.
You say that you're using some network to do like a kind of interpolation of your PDF between the points that you sampled.
It's not, it's kind of interpolation of the PDF, but not in the usual way, right? Because I don't have the value of the PDFs. That's the difference of the generative models. It's different from a usual emulation.
You have sampled PDF in some points, and then in the network, you want to know what is the value of PDF outside of these points.
No, actually, I want to know the PDF. Or more specifically, I want to know how to sample from this PDF. This PDF I don't know, right? I only have implicitly in the simulator. So I want to be able to learn this PDF. For example, here, right? What's the PDF of cats playing chess? Don't know, right? It's a very complicated PDF. But if you train these generative models, we are able to sample from this PDF, even without really knowing the PDF. So here's the same thing. I want to be able to sample from this PDF, even without really knowing this PDF. For the normalized flows, it's especially good because I can actually know the PDF. So it's why the normalized flows is a better generative model for this application. For example, the diffusion model, like the one here, we don't have access to the values of the PDF for a given data. Okay. So that's the idea how to do it in Cosmo. Yeah. So just to summarize the generative models we have, those four are the main models. Okay. The first one, which was the old standard, was the generative universal networks, where the idea was to train one network to generate an image from noise, and another network to discriminate if this image generated by the first network was a real image or a fake one. So the idea is to put both networks to compete and to get better at each iteration. This is very good, but of course we don't know that the PDF here is completely implicit in this case. A second option is to use variational autoencoders, which is a variation of autoencoder, okay, where we have an initial image or initial data here that we go to a latent space which is much smaller. Then we have a decoder that go back to the original image. And the idea of the variational part is that we constrain the distribution of the points in this latent space to be more compact. So it's easier to really generate images. And we also have the diffusion models, which is the one that generated the cat. And the idea here is to start with an image or a data and apply a Gaussian noise in each step till we have basically only noise. And then we train a neural network to basically remove the noise of the image. So in the end, you can just book some noise, apply the neural network, and take some image that makes sense. And the one that we are going to use now is the normalizing flows, okay? Flow-based models. And what's the idea of the normalizing flows? The idea is that we start with latent space, with variable latent space, which usually is just sampled from Gaussian. Then we want to apply some transformation. That is the neural network in this case. Theta is the parameters of the neural network. So we want to apply this transformation to move the points here to the space of X, such a way that now the distribution of X resemble the true PDF that we want to get. Okay. So for normalizing flows, the trick here is to use the composition of many simple functions. Okay, so we also need to know how to invert this function, which is the inversion of each function here. And because of the change of variables, we can explicitly compute the final PDF. Okay, the final PDF is just a function of the base PDF, which is a Gaussian, that we know how to compute the log of the Gaussian, plus the determinant of the Jacobian state transformation. So here there are two very important points that we need to know how to invert the transformation. It's not trivial from neural network. And we also need to know how to compute the determinant of the Jacobian, and we need to compute it very fast, okay? Because we need to compute for each step in the training. So one way to accomplish it is using, for example, the masked autoregressive flows. With the idea is that we have the Latin space here. So each point of the Latin space is mapped to the next layer, okay, or to the final here, X. So each one of this transformation is going to map this to this in a linear way, where the coefficients of the linear transformation are given just by the previous parameters, the previous components of the variable. Because in this way, you can see that the Jacobian is triangular, okay, because this guy is completely independent of the guy that comes after it. So the Jacobian is triangular, so the determinant of the Jacobian is just the product of the diagonal. So it's very simple. In this case, that we assume that you have like an exponential of alpha, the log of the determinant of the Jacobian is just that's over the alpha. So it's trivial to compute the Jacobian, and it's also, of course, trivial to compute this because it's just that straight line. So this is the masked autoregressive flows, which I think that's the standard way to normalize the flows. But you also have other options, okay? The main point that you really need to address here is to make the Jacobian to be trivial. That's yeah.
How do you compute the alpha E and then?
Yeah, this is the neural network, okay? Alpha E, for example, for X, to compute Xi, the alpha I will be given by the as function of all X's before I. So from 1 to I minus 1. So you have a neural network where the outputs are kind of the name masked here is because the neural network is masked. Such way that the outputs here, for example, the first output is independent of all inputs here. The second output depend only on the first input. The third one only on the two first. Okay, so you have to put a lot of masks in the neural network, and to get this triangular Jacobian. Okay, so it's the alpha and B is just neural networks, the outputs of the neural network. Okay, any questions so far? Okay, now what's the continuous normalizing flow? Okay, the continuous normalizing flows follow the same idea, but now we, instead of doing like K transformations from the linear distribution, we do K transformations. Now we basically do infinite null transformations. Okay. So we have now solve this ODE here, where now the neural network is not the transformation itself, but is the vector field that gives the transformation. Okay, this is basically what's the name? It's a neural ordinary differential relation. So the same thing that we have here, the change of variables for the PDF in the continuous case is also given by another ODE. So in the end of the day, we have to solve this system of ODEs, one for the trajectory that goes from your Gaussian to your final PDF, and one for the PDF itself. Actually, we solve backward because it's simpler, because of the initial conditions, because we know that in the end, the variable must be equal to your variable, your data, and the difference between the PDF is just the true and the final. One should be 0 because one should actually roll it. Okay, so we have to solve this, but now F here is a neural network. But the main point here is that first of all, the inverse is trivial because it's a first order ODE. So the solution is just the integral over the vector field, and the inverse is just actually to the other side, which is integral. So here is the inverse, and also this term here, which is the trace of the Jacobian, it's also trivial to compute using this trick here, that the trace of a matrix is just the expectation value of epsilon times A times epsilon, where epsilon is a normal variable. And this is faster than computing this trace because of the auto differentiation that we can use for JAX or PyTorch. Okay, so because of numerical facts, we can compute this trace also in order n, the same way that you could compute this trace in order n. Okay. So here we have how it should work, right? We start from a Gaussian in t equal to 0. Here the times is meaningless, okay, it's not feasible. And I have some vector field that's given by the neural network, and we want to go into this the diagonal PDF. So here is a git how it works. Okay, hope you can see. But basically, this is the target PDF. So it's just points that follow this distribution, which is basically 1 in the cat and 0 outside. This is just the GitHub cat. So we have just a sample of points here. Okay, we don't know the PDS. So we start here, just from a Gaussian, it's basically a sphere here, and following this vector field that of course evolves with time, we can get a very similar distribution of points that we have for the target. And because we are using normalizing tools, we also have access to the PDF itself. So here you have the values of the PDF, and here a sample from this PDF. So, yeah, that's
Target is your simulations.
yeah. For example, yeah. Here is a very simple, just a 2D data, just an image, just following. But in for cosmology would be the parameters. So, okay, the main advantage of the continuous case in contrast to the discrete case is because it's much more representative. It's more it's stronger. Okay, it's been reproduce better the distributions. Why it happens? If in discrete case we saw that the transformation would be something like this, okay, where the component y at some iteration t plus 1 will be given by the component y in some iteration t times this alpha function, which is just a function of z up to I minus 1, okay? And the same for me, which is how we make the Jacobian trivial to compute. But now for the continuous case, to use for the first order order, just to get some information, we see that at order t, t plus 1, sorry, it depends on all the vector at order t with a very complex neural network here. And here you can see an example, okay? We have 3 examples of distributions here. This middle column is flow is just a usual normalizing flows, and fjord is the continuous normalizing flows. And you will see that the continuous normalizing flows is especially good to reproduce the tails of this that are rolled here. You see that again, especially in this case here, we have much better behavior for the tails, which is very important for some statistics in cosmology, for example, the density, where the tails are actually the hard part to describe. Okay. So just a quick thing that I don't have much time. So basically the number
We are flexible, but just so you have an idea.
okay, the number of functions evaluations because we have now to evaluate the neural network many times, because we have to solve the ODE, with for example, or something like this. But one thing is that the number of function evaluations is not a function of the dimension of the problem, which is very good. So we can go to very high dimensions that, and we don't need to compute more times than the vector field. And this is just a technical thing that you can also apply this polynomial regularization to make the vector field simpler. This increases a lot it speeds a lot all the process because now the OT solver can make larger steps, okay, because the derivatives are smaller to find derivatives. And also it's better to avoid overfitting.
Brilliant. So since you're trading the, let's say, in order 10, you have to run 10 epochs of discrete transformations. Here you say that your order is now not 10, but let's say you have a polynomial of order 10.
Yeah.
That is essentially,
Yeah.
you're trading that sense, right? You don't have the epochs anymore. You're just fitting for these 10 parameters of the continuous fit.
No, you have the epochs for the training the neural network.
Okay, but you don't have the 10 discrete transformations. That since you have when you have a polynomial of order 10, it will be equivalent to the same number of parameters at the end, right?
So
How do you find those? You do have a kind of you are saying that the function that you're fitting has to have some form, or do you leave it completely open?
No, it's completely free.
Sorry, then I didn't understand the example there of a polynomial.
This is just an extra term that you can put in your loss function.
Oh,
In addition to your Kaelo versions to make the vector field simple.
okay, then.
But you are completely representative of your problem.
Okay, so then
What
I understand that is that your vector field has in principle infinite parameters. How do you fit that in each epoch of your training?
the parameters of the vector field are the parameters of the neural network. You just run a gradient descendant over the longitudinal or the OT solver, okay? Because at the end of the day, you have to discretize your OT. And you can just, for example, this is a possible solution of the ODE, right? So here you could just run a back propagation here because you have your neural network and you know how to go from one step to the other. But of course, you have to back propagate harder 1 2 times. So it's of course not more complex than in this case. So yeah, this is just a concrete example of how good this is to reproduce some PDF. This is the 10-dimensional completely run PDF that I just painted. But you see that the red regions are the red curves are the data, and the blue ones the ones recovered by the conditional normalized, the continuous normalizing flows, with just I don't know 10 apples and with just 1,000 data points. So it's really good to basically reproduce any PDF with any here. So another thing that's good to discuss now is that I just took this example here and take the two first components, condition them to the other 8. So now I try to compute some conditional PDFs, and here's just to show why the joint is not very good. Here the 3 colors here, I'm just taking the joint PDF and try to use ABC to make that slice, okay? Because to get the data, I need to make a slice, and to make this slice, I have some widgets for this slice, right? But the problem here is that I have to make a slice, and I use dimensional space. It's not very large, but still we see that the convergence of the final posterior is very, very slow steps. And these red regions are really very expensive to get. So using some conditional continuous normalizing flow, which is the blue region, it's
Sorry, conditional what? What? Sorry.
here is the condition. We are trying to take the PDF of the first 2 dimensions, conditional to the other 8. So very simple example. But just to justify why I'm going to use the conditionals for the function. Okay, it's just to talk about very quickly about the condition, but it's just the same thing, but now we have to put some extra conditions y. But it's the same problem, and now the original PDF is also conditional by this condition y. For example, in cosmology, that would be the cosmological parameters, and y would be the data, like the force spectrum, the density grid, or anything like this. So here just to describe the architecture that I'm using for this continuous normalizing flows case. So we have these concatenation layers, okay? Basically gets the output of the previous layer here. And some conditional, for example, the base bridge or the core spectrum are the two things that I tested. And also get the time, okay? Because the vector field is also a short time. So I pass the condition to some neural network for the grid convolutional one for core spectrum just a multi-layer perceptual. And then I concatenate with the output of the previous layer, pass to a multi-layer perceptual, have some output that I multiply by the time passed by a multi-layer perceptual, and with the time passed by another multi-layer perceptual. Okay, then now I have the output of this layer, and I combine many of these layers to get my vector field at some time t. If for some parameters theta and some conditional for the base grid or the core spectrum. So the conditions that are entering in each layer here, not just in the beginning, which is how you usually do for the ISO normalizing flows. Okay, very quickly. Okay, so I run some Gaussian fields. This is the likelihood of a Gaussian field. It's not a Gaussian. It's very nice because you can see here that the Gaussian is not exclusive. So when I compare the units MCAC with the continuous normalized flow, that SPI both give basically the same posterior with respect of the TMC with the exponential that gives a smaller posterior because it's actually the likelihood for the field. We can run for thousands of run the inference for thousands of realization because it's very fast. So then you get something almost a Gaussian here. Another nice property of this method is that if you don't train enough, we always get larger PS that are always not biased. So to train more, you get closer to true, but if you train less, you just get a larger errors, which is fine. Right? Okay, you have this is more technical, but just to see that we have to apply some augmentations to the data because we have to impose the symmetries of the grid in the case of the grid here. And maybe this is slide that show that the results are very robust to change the neural network. For example, if you double the number of layers for the compression, or double the number of layers to compute the vector field, or reduce the number of simulations used to train by a factor of 3, you basically have the same posterior all times in comparison to the dilution. So, okay, yeah, this is the hybrid that I talked about last week. But the idea is to combine this hybrid approach to generate the grids, okay, for the biased fields, and use it inside the continuous normalized flows to get the possibilities. But this is for the future. Here's just comparing with Paulo, showing that these emulators or the displacements that work better than Paulo. And okay, just to finalize the comparison, because there are a lot of other groups that are trying to do field level, first with field level. I think that the two main groups are the CMB group, but the problems with the CMB is that they have just a small number of simulations, just around 2,000. The simulations are very low resolution. They have about 1 particle per megawatt particle. They are using the usual normalizing flow, so they have to compress the data before running the likelihood, the estimation, the posterior estimation. So it's also not optional. And they also have a fixed stochastic part of the theory because they are in HNP. And if you go to the left field group, they are just using theory. So they are very limited by the scale and also limit the stochastic part of the theory. So yeah, that's it.
So I guess we can use 10 minutes for discussion if we move into the next topic.
Oh,
Yeah.
so can you like, just a really naive question, so where does the, for example, the errors in the covariance or errors in the estimation of the whatever summary you're using entering these kind of things? How do you know that you are not, for example, over fitting the parameters and have like way smaller error flags than you should from a realistic covariance?
The covariance is implicitly given by the simulator.
Okay.
So all the information about the scatter is in your simulator. So of course your simulator was the right one. Yeah, right, that's the case. It's always the case. And we have this kind of properties, these methods. When we go wrong, we always overestimate the errors. We don't get, it's not proven, okay, but maybe we don't get bias constraints and we don't get smaller errors, with the exception of overfitting, but overfitting you can control neural networks quite well in this case.
Right, so there is no way to put like an input covariance. Like, for example, if you have like a galaxy survey that has like a fixed covariance, you cannot.
No, we'll have to consider in later.
So you will have to construct something that looks like the covariance from the.
Yes.
Okay.
Yes.
So, coming back to this question, so let's say that you know exactly what the, let's say that you can find this, your distributions precisely well. Let me ask, maybe there's something that perhaps I haven't understood. So suppose that you have your set of real data, right? And this is your real data here. And of course, you can always find what is the maximum likelihood or whatever, maximum probability in this case, point that corresponds to this or the region around this. What I still don't understand is how do you go from that to quantify the uncertainty around this area in parameter space? You need to know, in some sense, when the probability is not, you need to have a metric for how far away you are from the peak. This is where it's not entirely clear to me that where it's coming from in this approach. Maybe I haven't understood something about this. I mean, you are always saying that you're finding the probability, but I mean, we're not talking only about probabilities. We're talking about distances between points in your parameter space and having a sense of how far they are. This is what defines your global probability, right? So this is what I still don't understand in this approach. By the way, I think it's a general question about normalizing flows, not necessarily about continuous normalizing flows. How do I assess the not goodness of it, the badness of it? I mean, when you are far from the best fit, where is this distance coming from in the end? Because I'm not seeing this anywhere, but it has to be somewhere. There's no a priori metric for this in this normalizing flows approach, right? But it has to be coming from somewhere.
Yeah.
Otherwise, you don't have a notion of distance in that sense, right?
Yeah.
Where is this coming from? Maybe this is
From the simulator. Okay, your simulator knows if one data is far away from another data, right? Because your simulator knows how to go from parameters to data. Your simulator knows how to go from one parameter to many data, and how basically knows the covariance, right? The covariance and also the higher end by the functions. Simulator knows everything, basically, right?
Right. So you have to make sure that the resolution of your parameter space is then reflected into enough data points that you can figure out back when you move by this much, the data moves by that much.
Yeah, because the metric you are talking about is just the line, right?
Yeah.
And the likelihood is just a simulation. So
Okay, I think I get it. Okay. I think I understood at some point, but then I forgot. And it's clear.
Then I have a sort of same question, but in more basic level, more naive, right? But I mean, in the Monte Carlo, I know that if I have a drawing, I prefer here, what I should do. the convergence. Once again, the simulator, what is, I mean, I really don't work. So I mean, really from a broad perspective.
Basically, I think that nothing, but because you are training a neural network to learn your PDF. Of course, if your neural network is too weak, we cannot learn your PDF or final PDF. You can guarantee that your neural network converts to a local minimum of the loss, but you cannot guarantee that it converts to the true PDF. And we know that's actually the case. For example, if you have just a small set of parameters, a small set of, you simulated just a small set of parameter data, you cannot really learn your PDF, right? So you convert to a raw PDF. But the point is that we observe that it always converts to a larger PDF. And the true PDF is always silent. So usually we are not biased, but it's again, it's not proven. It's just empirical constatation. But yeah, you not guarantee that you convert to your right PDF. But we hope that with infinite simulations and with infinite neural network, we should over.
No, you're not going to, if you do, let's see, in the example you showed, you did 1,000 samples of your data. And then you run a few iterations of your neural network to try to get the PDF. I can be sure that you're not going to be overfitting if you do like an infinite number of iterations of your neural network, then you will produce only the data that you submit. Because they don't have an infinite number of simulations. Yes, can you show get the track that
This,
yeah, like for instance, also very small filling dots, they are just because you have a finite number of simulations, right? And this not probably is a true PDF. So I can be sure that you don't go into overfit.
we are not sure, right? It's the problem that we always have with neural networks. We have methods, for example, I didn't talk about this, but for example, this augmentations. It's a way to avoid overfitting, you know. It's here is the log function. The red line is the log function for the validation. The red line is the case that I don't apply any augmentation. So you see that you get some decreasing and then this just diverge. So we are completely overfitting them for the training. The validation is completely wrong. But if you will start to apply some augmentation, for example, rotation or shift it in our next degree, you see that the loss now gets better and better. And for example, the blue line is when you apply both rotation and augmentations. So now if the loss of the validation is better, means that probably you are overfitting less. Okay? We cannot guarantee that I'm not overfitting at all, but I can try to overfit less. For example, applying augmentations, or for example, applying dropout layers or just techniques of neural networks. You know? So I cannot guarantee that I'm not.
But yeah, last. Sorry,
I think that.
I just wanted that if you introduce. What's what the regular DPI introduce next year? That will just finish the. You are not for that. Because in case you are sure that that word will.
Yeah, you reduce the degree of overfitting, right? But you cannot ensure that you are not overfitting. Because even the dropout layers, you have to choose some probability of dropout. And of course, take this probability very low, you can overfit it. To take very high, you can overfit anything level. So we don't know what's the best. We can try to get the hyper parameter, but it's always challenge.
okay, very last.
Oh, yeah. So you didn't mention nothing about like how to validate these things, how to validate these PDFs. And then what about for images? Do you have already any idea how to do this validation for image generation? because we know how to do with the PDF, so it's like the probability distributions that we have in this traditional ways, but what about for images?
Image, you mean general image like the cat?
Yeah. Because every time that we regenerate these fields in our case as cosmologists, we always try to see if you're right, going back to, I don't know, to power spectra or anything else like this. But how to really validate in machine learning like ways to do this? Do you have any idea?
General.
It's still it's an open question, it's just like I would like to know your opinion.
Yeah, I think that the only thing that I can think is you need something like a validation test set. And try, for example, here you could try because you want to go from the get to the noise, right? So I can take my test set with some different images, go to the noise and try to come back, see if I recover the image. So something like the inspire error between the two images should be a proxy of the quality of my network. This case, or actually in the case of the generative models.
Yeah.
But of course, it's kind of arbitrary. Some number.
Okay. So again, thank you for the meeting. Well, introducing more as in 30 seconds. Update camera. Those who have introduced themselves earlier, can do it now. You would like not going to introduce yourself. Just say your name, who you are, what you do in this.
Yeah, I am as
Okay, so just like
Aqui, que acompanha solo da música, sou da graduação da física, e eu estou pensando no evento, estou aqui para ter uma visão de mais geral sobre inovações e instrumentar.
beleza. Para mim.
Matheus, eu não sou estudante, aluno da São Paulo. I'm currently preparing graduate students physics, and I'm doing taking a shading cosmology, so I'm here to learn about this. My name is Jens, I'm currently working with Paulo, since just got into program last institution programs. I already have experience working with machine learning at a very financial level, so in general, just cosmology. That's why. That's why.
Hi, I'm Andrew. I'm a postdoc at UCAF and just visiting Sao Paulo, so see Ricardo. I work with gravitational waves, specific data analysis probes of dark matter.
I'm Marcelo Vicente. I'm a PhD student at University of São Paulo. I'm also for marriage. I'm working mainly with detection of galaxy clusters and bubble clusters. Detection of galaxy clusters and bubble clusters from automatic surveys.
My name is Gustavo. I'm a PhD student from Universidade Federal do ABC. I study cosmology with Professor Schenk.
Hi, I'm Pierre. I'm a master student in USP, and I'm working with Layer 2, and I'm working with some ultra compact galaxies, applying machine learning to separate them from stars in foreign space.
My name is Felix. I'm a PhD candidate, also work with Legrand at USP, and my project is to decompose automatic redshift to study the large scale structure. High class.
So I have a very ambitious product because they want to do my work. Plus, I wanted to have some 8 minutes in there to present the latest result of the data with the data. It's a kind of spin-off of the journal club, so it's nice if we can discuss the problem. I try to manage to have a plan to develop. So we want to introduce what is my background. What is the gravitational lensing of the CMB, and how can we measure it? And then the measures of cosmological constraints with CMB lensing, and how we can improve our simulation experiments. I apologize for people that don't have so many don't see now because it's a place that's in it. And then in the time I will talk about application and CMB lensing, and then the training was a new year results from the questions that we can discuss together. So here is a timeline of the universe. So after a period of inflation, the universe was very hot and very dense, and the protons were trapped inside the plasma of the elementary particles. And after some time, like almost 380,000 years, the universe cooled down, and the atoms were able to recombine. So, we were able to combine into hydrogen atoms, right? The universe became just solids. So first there was this period of inflation at the very beginning of the universe, where a very small quantum fluctuation in the field were inflated to millimeters length scales. And then it's evolved. It's a matter of photons what the universe was in the past. And then there's a moment where the matter combined, and the universe became transparent, and the photons of the cosmic microwave were limited. So these photons did travel the universe today, and we can observe them. And it gives us an image of how was the universe very early. And later on, with the formation of the dark space structures, so galaxies and galaxy clusters, as we see today in the universe. And this distribution of matter in the universe will deform the line of the CMB photons by gravitational lensing and later.
So can you translate your redshift those back time?
Yes. So that's today. So that's realization is around HF10. Recommendation is 1,000. This people are talking about the chips that they want energy scales. I'm sure. The information of galaxies for now with JWST, we're able to go back to 10, even 12. So the earliest galaxies that were observed. Just like last researcher surveys, they go to so there was all this period, there was no light, no pin, because there was no stars. The top stars formed 1 year later, that start to recognize the universe. There's a gas that was made out by the very strong light. And this, if you were able to see in the microwave domain, your eyes will see the sky like this. So homogeneous condition everywhere in the sky, and the temperature, perfect Lagrangian temperature of 2.7 Kelvin. And this is the light of the CMB. The problem of the CMB, so when they were decoupled from matter, they were much hotter, right? They were very hot. But then the universe cooled down and expanded, this light cooled down also. So it's very cold. Okay. And if you increase the contrast by a factor of 10,000, this is what you observe. Okay, so very small inhomogeneities in the distribution of photons. There are some parts. So this is an image of the sky. Okay, so the image of the sky is a sphere, and put it in a black sphere, right? And there's some parts that are much hotter in red. Some parts that are very cold.
So this with monopole and dipole subtract.
Yes, exactly. Yes. This usually subtracts the monopole. So the so the dipole is due mainly to the velocity of the Earth with respect to the CMB. So you see some Doppler effect, right? You see from the ground more incidence of Earth on both sides. So the idea is to and you subtract it, and you see some small inhomogeneities. And this was observed as a long satellite. So So this very small fluctuations, okay, they translate into fluctuations, the density of matter at the moment of decoupling. Okay? You have some part of the areas that are a bit more dense, some part that are a bit less dense. And this is sourced by the primordial fluctuations in the electric field that then evolve in the plasma of the particles in photons. So you have the matter that wants to collapse with gravitation, okay, it's attracted by gravitation. And you have the photons that are trapped by the matter that want to push away by the radiation pressure, okay. So you have these oscillations, and this is called the baryonic acoustic oscillations. And then, when there is a decoupling between the matter and photon, this the matter is photons, the matter are frozen, they don't actually anymore. And this is what you see, it's photons you see. Okay, so then we do how do we do science with that? We compute the power structure. So just introduction, if you're not familiar with it, what we do is then the Fourier transform on the sphere. Okay, so instead of doing Fourier transform on the plane, we got the sphere and we do a multiple moment decomposition. Okay, with this spherical ALF and got all the information that you have in your field. So here X is the temperature of the CMB and L is the direction of the sky, and then transform this with this spherical harmonic coefficients. And they are parameterized by two numbers. So the first number, L, gives you the order of the decomposition. So you have the monopole, the dipole, quadrupole, etc. And then the M gives you the orientation of this decomposition. Okay. What you have to remember is that if you increase the L, then you go to smaller states. Okay. The small L is very large scale, and the large L is very small scale. And then, if you have a statistically Gaussian field, then all the information of your field is contained in the angular cross spectrum. This angular cross spectrum is variance of your ALM, average over all the N, so for a given L. Okay, for a given L, you average over all the N, and you get this variance here. So this is the angular cross spectrum that we use. And this angular cross spectrum, the temperature of CMB is like that. So here, you have the large scale on the left, small L's, and the small scales, the large L's, and it gives you the variance as a function of scale on your CMB. And you have these typical shapes here, these oscillations that are sourced by this pattern of oscillations, this baryonic acoustic oscillation in the primordial plasma. Okay. And the red dots are the measurement of the block satellites, and the blue line is the fit of the lambda CDM model on these dots. As you can see, it's a very good fit. You have the difference in the model panel. Okay, so this is gravity pressure condition. Just said. Okay, so then the CMB is also polarized. Okay, so the photons of the CMB are polarized, and this polarization is created by the perturbation in the distribution of electrons at the moment of the combination. Okay, and what we do usually is that we decompose this polarization into two fields, the E and the D modes, by analogy to electromagnetism. And you have the B mode, the E mode, sorry, that don't have any curve, so just like gradient modes, and the B modes that don't have any gradient, just curve line pattern. Okay. And the interest of this is that by theory, we know that the density perturbation will create only the E modes. They don't create any E modes. While the tensor perturbation, which are the gravitational waves, will create the E and B modes. Okay. So if you're able to observe the B modes of the CMB, then you can get information about the gravitational waves at the moment of recombination. Okay, so very early gravitational waves. And these gravitational waves, they are created in terms of inflation. Okay. So during inflation, you have this period where the universe expands very fast, and all quantum fluctuations can stretch to a millimeter scales. But you also have a quantum fluctuation in the big tree. Okay. And this creates gravitational waves. And then you can see the B modes of the CMB much later. And this is the cross spectrum of the polarization. So in red, the polarization E modes. So this is a simulation, okay, it's not a data. In red is the polarization E modes, and in blue is polarization B modes. So you have two contributions. Okay. And so there is one that is So there is one that is due to the lensing. So these are the secondary remotes that are created by them, that are not the common remotes that we just now. And then you have the primary remotes. And because we don't observe them, we don't know what is their amplitude. Okay, we don't know yet what is their amplitude, and they depend on the parameter pairs, it's called the tensor to scalar ratio. And here I show two possible values. The R is big or R is low. And if it's big, it's dominating over the ones that are created by lensing. Like one, if it's small, it's totally dominated by the lensing. Okay. And then a few words on the standard cosmological models. So the
Sorry, so if R is less than 10, we say you never see it in remotes. The effect of gravitational waves.
Yeah, so I have a forecast at the end of the talk. Okay. Sure, what we can measure in this. So the standard cosmological model is under CDL. We have 10% only that is composed of ordinary matter, so that's it stars, for targets. And then we have 25% that's in dark matter, so it's a missing mass that we know in galaxy, in cluster galaxy, and interact only in the gravity. And then we have 70% that is in dark energy, that is responsible for the late time accelerated expansion of the universe. So we know the universe is an expansion, it's also accelerated. And to fit the curve that I just showed, we only did 6 parameters. So H0, which is the expression rate today, is 1 parameter. Omega D and omega C is density of variance, density of dark matter. Tau is the parameters of the sets, the amplitude of the periodization. So this periodization also impacts the CTP photons because it scatters them again, so it becomes the potential. And then we have 2 parameters that tells you the core spectrum. The fluctuations are term inflation. The one is the amplitude of the core spectrum, AS, and then MS is a tilt for this core spectrum, it's the inflation. And with just these 6 parameters, you're able to fit the curve that is shown. I will also talk about sigma 8. It's very similar to the AS. It tells you the amplitude of the matter core spectrum. And then there are some standard extensions to it. Some of the nuclear mass. Sigma and mu. So we know that the neutrinos, they have a mass from observation of the oscillations of the neutrinos. But we don't know the absolute value of their mass. We just know the difference between 2 different mass states. And in cosmology, you're able to measure certain tokens. And then there is this tensor to scalar ratio, so the one that sets how much Gaussian ways you produce an interpretation. And then another one is the dark energy equation of states. So if dark energy is free, you can write this equation of states, and the parameter is W here. And this I will talk not for CMB lensing, but for the PA results. Okay, so some open questions in cosmology. What is the nature of dark matter and dark energy? What is the mass of the neutrinos? Is inflation happen how? And to answer all these questions, we need a new surveys with improved statistical power. Because this is the limit that we have now for CMB observations. So we have a different observations. So there was a Blanc satellite that observed really the large scales and the small scales in temperature. And can get the large scales in polarization imode is not great and didn't get anything for imodes. And then you have the SPT and ACT that are ground-based survey that went to smaller scale temperature polarization. And then we have observations that are targeting specifically the imodes. So they say and polar pair. Okay. So as we see, we're still very limited by the limode. We don't know much about the limode core structure. And here it shows you a possible value of the surrounding limodes. And we are going to have a lot of observations in the coming years. So for CMB side, we have next year, summer, we have the start of the Science Observatory that will observe CMB at a small scale. Then we have CMB stage 4 and Legrand. CMB stage 4 is kind of the follower of Science Observatory. We observe a very small scale CMB and also the polarization modes. And then Legrand is a satellite that we'll observe. So to go to a very large scale, we need to go to space. This is a satellite, very large scales. And then from the galaxy side, we have a lot of things that are coming up. So there's a disease that already published first stage is that week, so generally that's now taking data. And next year there will be LSST, and in a couple of years it should be also government telescope.
Another question is okay. Or can you explain like why the constraints are very good at large scale but not small scale or vice versa?
Why? For the large scales on the ground, so this part here, you're limited by the atmosphere. So if you're a telescope on ground, you don't get a lot of function at very large scales. You need a satellite like Legrand to get this part here. And then the small scales are limited by the resolution of the instruments. So typically the size of the beam that you use to show the CMB. La space we are considering also, so the bigger mass, very efficient. So now we talk about what is the gravitational lensing with CMB and how we measure it. So gravitational lensing, the deflection of the light by mass. Okay. So if you have a galaxy in the background, and you have some mass in the foreground that can be galaxy cluster, then the light will be deflected. Okay. And the deflection angle is proportional to the mass of the object.
Lens.
Yes,
Mass of the lens.
mass of the lens, yes. And for the CMB, the same thing, but here the CMB is an extended source in the background. Okay, so here is the showing so the same diagram in the inverse, and here you have this big opening of quantum photons, and the photons that are emitted at this moment, the cross all the universe will come to us. So if there is a distribution of galaxy in the background, then they will be deflected by this same distribution. Okay. And this is what happens in the CMB if you lens it. So here are three simulations of a CMB field. So temperature in the top, polarization E mode in the center, and D mode in the bottom. And if we put this to a simulation of the lensing, this is what happens. If I shift between the two quickly, you can see that the temperature T and E modes are distorted, and you create some D modes. Okay. So the distortion of the temperature you can understand because we're detecting all your light rays. Okay. And the polarization, the D mode, what happens is that if you have a polarization pattern that is without any curl at the beginning, if you distort your polarization pattern, then you create some curl. Okay. So you create some D modes. And this is how you create the secondary D modes that will dominate your signal if you want to look for rotation. Locally, what happens to the CMB field is that you will magnify or demagnify your power spectrum. Okay. So if you have a lens in front of you and you have the CMB behind, then all the scales will be enlarged. Okay. So you enlarge all the spots that you see here. So the power spectrum will be shifted to the lens, to the large lens. Okay. And the opposite, if you demagnify, so look at the void, then you will see everything a bit smaller. And so it will shift your power spectrum to the small scales. So locally, you shift a bit your power spectrum on the CMB. And this is what happens on average on the sky. If you average your power spectrum everywhere on the sky, the color code here is a function of the amplitude of the lensing. Okay, if you have zero lensing, it's blue. If you have a lot of lensing, it's red. And you see that you smooth the peaks of the temperature and polarization. Okay. And this you can understand with the fact that if you shift randomly to the right or to the left everywhere in the sky, and then you take the average, you will smooth these peaks. Okay. So this is what happens on average of the CMB perspective. Okay, so now how do we do to reconstruct the CMB lensing field? Because we don't know what is the image of the CMB before it was lens. Or we know it's the one that we see, that is lens. Okay. So the idea is to assume that we know a bit like in the swimming pool. If I ask you to reconstruct the distribution of the waves at the surface, one hypothesis that you can make is that the size of the lines in the bottom are all the same. And all the lines are parallel and orthogonal. And this is the same for CMB. So what we do in practice is that we assume that we know the statistics of the CMB. So we don't know exactly the realization of the CMB, but we know its power spectrum. Statistically, we know how it should look like. And we will look at different parts of the sky and measure the power spectrum in different parts. And then if you see that it's shifted to the right or shifted to the left, then we know there's a lens or no. Okay. So this is how we do in a sketchy way, how we use only the construct the same lens. Okay. In practice, if I go into the formalism, what we use is the fact that the stimulating will create some correlation between different states. Okay. So if you have a correlation between the lens temperature field, the at different multiples and different temperature, then you have some correlation that depends on the spine, that is your lens temperature. If your CMB is statistically isotropic and Gaussian, then normally this graph is zero. You don't have anything. But because of lensing, you create something that is proportional to the lens. So we kind of invert this relation by building an estimator that will integrate over all the scales of L and BL to get an estimate of this lensing potential. Okay. And this is what we call a quadratic estimator, because you combine two different maps together to get an estimate of lensing potential. Okay.
So how do you know the F?
And the F is by you know what coupling you will create in your multiples if you have some lens.
Okay, you know it.
Yeah, it's an analytical expression of the lens please. So your CMB lensing field, which is estimated here on the left, will be a 2-point correlation function, a 2-point function of your CMB maps, okay, because you compare two maps together.
So you assume that all correlations in the CMB is not less.
Yes, that's a.
So if you have another source,
Exactly.
for example, your tension weights,
Yes.
you contaminate the site.
Yeah, it's one of the big issues of this estimator is that you catch all the stuff that is not lensing in it. And there's a lot of work that is done to make it focus on other sources of contamination. So the main source is extragalactic sources, like galaxies that emits in the same frequency as the CMB. They also create some non-Gaussian signal in the CMB map, and your estimator will catch it, supposing it's a lensing. So it will also pay it.
Non-Gaussianities are negligible compared with other combinations.
Yes.
Yeah.
Yes. So, okay, so this is what was done by Planck. So here it's a mass, it's a map of your density field along the line of sight. So here you have all the matter in the universe integrated along the line of sight. Okay. So there's a lot of information about how the universe evolved and how it is so, what is its complexity. So then you want to do some cosmology with it. Usually what we compute is a perception. Okay, so it's a 2-point correlation function of your map. So here it's 2-point correlation function of the CMB lensing is a 4-point correlation function of the CMB model, okay, because each one is a 2-point function. So this object, the construction of the lensing field, is a 4-point correlation function. So inside this, there is different correlations of the handles. There is one that is a signal that we want. So it is a CMB, so construction of the lensing function. And then you have some random correlation to different scales of the CMB that look like lensing, but are not lensing. For instance, if you have some spot, of the CMB that is randomly not spherical with a bit elliptical, then it will be contaminating your signal. And the thing is that this we know analytically we can compute it because it's a 4-point correlation function. We can put the 4-point correlation function of CMB and get both contractions and get these biases. So there's what we do is that we expand it several orders. Order 0, 1 remains, not order 1. And this.
Sure. What happens here if you have a primordial torch spectrum? For example, if you have a large violation, that generates some torch spectrum.
Yeah.
What's the impact here?
So for this, we have to know exactly what will be the coupling that you will generate in your CMB. If it's exactly the same as the coupling of lensing, then you're not lucky because then it will be very similar to lensing. If it's a different coupling, then we have some tools to try to differentiate. So you can do an estimate with a different L, that is the coupling of your effect you're looking for. and then do another paradigm estimator for this effect and see if you have something that. So this is the noise that we get for the measurements. Okay, so the signal we want is a black line, the CMB lensing pore structure, and the different lines here are the different nodes that you get for different combination of maps. Okay, if you combine temperature and temperature, you get the red line. This is why you get the most signal. Okay, you can also combine temperature and B mode, temperature, D mode, TNB, TNB. So you can do different combinations with your polarization of your maps. For Planck, what dominates is the temperature one, but then if you combine the time together, you get the minimum variance, okay? And you get the breaking, yeah.
All of these is just at the estimator level, right? It's not just a theoretical computation of the curves.
So this is the theoretical computation of the curves. You can get the theoretical.
So how do you do the theoretical then, or correlation of the things?
So you can do. Is that you do like a first order, you do Taylor extension. Okay. Say that the length temperature P is equal to the advanced one plus some displacement. And by then of 5 and okay.
Oh, this is placed and you don't know it, or it's a way to compute it, or you estimate the displacement from the maps that you see.
So this is just at the theory level that you're doing. So you don't know, you just do an expansion, analytical expansion of this, and then you know that your estimator phi will be an integral of two temperature maps. Okay. And then your 2-point function of the phi will then be a 4-point function of the temperature maps.
Okay, so then I have another question there.
So schematically speaking, I didn't drive also because it's
Right. So what happens with the, for example, the 4-point connected between all the T's and not the.
Yes, so that exactly is the first order and zero minus. So there's a zero forward. So if you do a connection between all the T prime, T prime, and all the different disconnected contractions like that, then you get the N zero minus. Then this expression makes sense.
Okay, good.
And then you do the connected interactions and try difference.
So then in this picture, the CLs coming from these is just T with T prime, or
So the
like the CLs of not the noise.
yeah, you mean the CL55?
Yes.
Yes. So the CL55 is this one. That is when you do this contraction, so you contract grand phi here, and then this thing. Then you have 4 other ways to combine this together. This will give you the CL55. Then if you do this contraction here, like this. I remember that when I wrote this slide, I understood how I
That's fine.
and then you get the N1.
Okay.
It's
Yeah.
well, because we didn't see. I will go a bit faster, and then I will go into a functional measurement of CMB lensing. So what CMB lensing measure is a kind of tube in a 3-dimensional parameter space. So the amplitude of the matter fluctuation, sigma 8, the mean matter density omega, and expert solution rate of limiters. You can understand this as if you have big lens far from you, then it's the same as if you have a small lens Cosmo. So you have a geometrical degeneracy. So this gives you the generality between the start from again and Siemens. And then if you combine with VAO, so the standard ruler of galaxy, you break this geometric data generality because you observe the same equation that the different redshifts, and you get this constraint here in this orange area. And then simulation can also give you a constraint on the sum of the natural masses. So here are two simulations. So the same simulation at the beginning, but with a different value of the sum of the natural masses. On the left is without massive neutrinos, and on the right with a very massive neutrinos. And as you can see on the left, we have regions that are very dense, red here, the regions that are very underdense. Well, here on the left, on the right panel, it's a much smoother, don't have so much energy. And this is due to the fact that the neutrinos, they are fast enough to escape the gravitational potential wave. So if you have a cluster that's forming, the neutrinos will get outside of it. So the potential wave is a bit less deep, so it will go less fast. Okay? So the neutrinos will slow down the growth rate of structures. And this you can see is another core structure.
Oh, wait, I will just say the opposite way. No? If they are massive, they should escape less. So the massive neutrinos, they should smooth out more. Indeed, they smooth out less than massive ones. Whatever.
So the massive neutrinos, you see it like they don't contribute to the mass of the.
Okay, yeah. No. But right, they count and they smooth out.
Yes, it's a count, but they escape before the. And you can see it on this plot here. It's the matter flow spectrum. It's a P of gauge as opposed to the scales. We see the large scales on the left, small scales on the right. And here is the function of the mass neutrinos. So if they are massless, it's 1. And if they are very massive, you go to the red line. So you smooth with them the structures on the small scales. And this typical scale here is the scale of free streaming, the scale above which the neutrinos they escape from the potential. And there's also another question that we don't know the neutrino mass hierarchy, so it's either in the normal hierarchy. So what we measure is this two intervals, this interval and this interval, but we don't know if it's in this order or in this order. Okay. And here the minimal mass is 59 millielectron, and here the minimal mass is 100 millielectrons. And CMB is sensitive to the sum of the mass, okay? Because CMB is an integral of the distribution of matter. Okay? And here is a ratio of the CMB spectrum for different value of some mass. And the gray band are the CMB stage 4 constraints. So CMB stage 4 will be able to detect some of the. And this is also the constraints that we get today. The best constraints since last week, the results. Put young students. Okay, how can we improve on the generation experiments? So here I will talk about idea.
Sure. Yeah, one question. I think you are probably in small scales as well here, right? So can you also put constraints on first dark matter or just?
With the CMB?
Yes.
So I think we don't get to small scale enough yet to see specific dark matter halos. I think this specific dark matter you will be able to think about. You wish see it like in the shape of the halos.
Yes, yes.
So
that's my scales. Yeah, I don't know what's the DC of 3,000 L.
Yeah, it's not enough particularly to go to 10,000 to see. So it's not yet reachable even for CMB stage 4. But I think it's in the paper for the next one, CMB HD, as I want to put constraint on the dark matter halos by looking at this. So in 20 minutes. Okay, so how we can improve on the generation experiments? So this is the CMB stage 4 survey. So I should start at 28.2. This, and it will be composed of 2 surveys. One in Chile, that is a very large, wide survey that we look at the very small scales, both of the sky, Then the softball that we look at a very small portion of the sky that go very deep to try to get the polarization depot very accurate. And for sequencing, what we use is this one on the left. And the interest of CTP-SAIFR is at the noise level, we'll go for the block noise level, which is this one here. And the interest is that it is below the lensing induced beams. Okay. So you will be able to observe directly the lensing induced beams. And the interest is that these beams, they are created by the lensing of beams. So if you observe both the E and the beams, you can invert the relation and get an estimate of your unlensed beams and the lensing potential fields that created these beams. Okay. And this is achieved by some iterative estimators. So we introduce now. So the standard quality estimator that I showed before that was used until today for Planck and ICTP is suboptimal by construction because it uses only a 2-point correlation function in the CMB maps. Okay. And for CMB-SAIFR, we'll be able to go higher than that. And in practice, what we do is to try to maximize this likelihood. So it's a big likelihood. Where you try to find the lensing potential field, it's 5, but then 50 million pixels map that we maximize the observed CMB. Okay. And we do this by iterating. So we first get an estimation of the covariance matrix, then we compute the gradient of the likelihood, and it gives us the maximum of a posteriori height corresponds to this value of the likelihood. Okay. And this first step is in practice a qualitative estimator. Then what we do is that we iterate, we put back this phi in the covariance matrix, and this one here is called phi. So this gives you how the CMB are correlated given this phi that you estimate. And then you compute another estimate of the gradient, another phi, and then you go to the convergence. So in practice, you use higher orders to pay for one function of the CMB. And this is the result of some simulation. So here, the sampler is a well-structured quality estimator. On the right is the iterative estimator, and this is the difference between the two, between the input and the construction. And you see you have much less variance because this iterative construction. One of the problems is that we don't know what is the core structure of this now, okay? Because the quality estimator on the left is a 2-point function of the CMB. So the core structure is a 4-point function. You can again for the biases. For the iterative estimator, you have n-point functions inside. So the core structure of this is a construct list that you don't know how to get analytically. So what I did is to estimate, to assume that we can get this core structure heuristic way by iterating on the analytical core structure. And there I show that it works very well. So it's a dot of simulations. The deadline are my predictions. It's include standard estimator and coverage the iterative estimator. And this gives us a constraint in the neutrino mass. So here I demonstrated that we can get a first signal detection of the second neutrino mass in the minimal mass field by combining CMB galaxies and CMB lenses. And then I went a bit more realistic by using some simulations with some anisotropic noise. So as I said, everything that looks anisotropic in the CMB could be taken as lensing video estimator. This is a noise map on the first slide. So you see it's a green. And I show that you can get unbiased reconstructions. So I go very quickly because I want to do that. So here it's just the residual bias on your core spectrum of different non-fiduciary cases. Well. And then we went a step further by using simulations that include non-Gaussian density structure. So, and the low redshift is the nonlinear evolution of matter makes your field non-Gaussian. So this is the image on the right. We also used beyond the Born approximation. So the Born approximation is that you assume that all the deflection field can be computed along the line between the source and the observer, while in practice you have different deflections that happen at the So this creates also some non-Gaussian signal in your lens signal. And for the quality estimator, this effect creates some bias. So here the fractional bias in the core spectrum. In the range is a post-board, so it's critical deflection. In blue is the non-Gaussian density structure. And in the lines here show the value for different prediction for different neutrino mass. You can see that they can bias your measure of some. And the thing is that we're lucky in CMB because both of them can set very well. And the sum here is here. So you have a small bias. how big is bias for the derivative estimator, and it seems to be even better, at least in the scales below 1,000, where you have most of the signal. And above 1,500, we have a bit higher bias. With it, we can do and also advanced directives. So we're working on that now. And this is some prediction for the treatment of the real mass. The quantum estimator is a little bit biased. The derivative estimator is not. We will not talk about the inflation part. Just to answer the question. So if you have some inflation, found the remote in blue, and then you have the secondary remote created by Yansin, totally dominate the signal for some value of the units, for some value of the scalar ratio. That's what we can do is de-lensing. So we subtract so we have an estimate of the lensing field. And from this, we can get a template of how the lensing remotes look like. We can subtract it from our map to reduce a bit this secondary limits. Go to the red dash line. This makes your signal get out of it. And this is what we did for the interactive estimator. We show here the constraints we can get. So the dark blue and dark orange are without doing the de-lensing. And if you do the de-lensing, you get a smaller error bars. And these are different models of programs, and these are different values of the error parameter. And we show that we can get a constraints of 5 × 10⁻⁴ from error. And this is a very interesting threshold because most of the standard models of inflation predict something around 3 × 10⁻⁵. So this threshold will be able to rule out the standard inflation models.
Okay, sorry. Yeah, so regarding the last part, could it be possible that you can have maybe other sources of big modes besides lensing, or and keep your assuming that the limits are only produced by lensing?
Yeah, so the big definition from this measurement is polarization from our galaxy. Okay. From the dust of the galaxy that is polarized on the large scales. And it was actually one of the big claims of the bicep experiment 10 years ago that they have detected the remotes, but it's just a polarization of the dust. So there's a lot of work to be done to estimate the emission, and we will stay.
So when you mentioned that constraints, you already include the contribution from the dust?
Yes, yeah. Here it was some simulations with a different model of the dust. I mean, this is just a Gaussian model that this gets more and more refined. And you can see that here you have the small layers in the sense.
What prevents to apply to real data? The better mark of the lens.
So for now, the real data is not yet, so it's going to be the couple of years now. So. We have the latest measurements from the Violet cake, and you can see there are black crosses here, and they're just getting to measure the lensing limits. So they just put an upper limit on what is the commandant limits, but they don't detect it yet. And for now, doing the de-lensing part will not improve much because we still limited by analysis. But we wouldn't go below them. But in the future data release, I think what they're trying to do now is to combine already with the de-lensing from SPT to get a better measure. For now, it's not anything. Do you have any questions in the CMB study? So now I would like to have some more open discussions about DAISY results. So last week we had new measurements of the AO, and there are some interesting results of the dark energy question states. So I think it's a good place to discuss together. But let's see what are your. So my goal is to try to summarize these main papers that were published last week. And I also stole most of the plots and slides from the conference that I attended last week. I tried to put the names of the people that I stole the slides and taking credit for them. So what is BAO? So this happens in the fundamental plasma, right, before the decoupling of fundamental models. And if you have over density field on parts, then it will create sound waves to propagate in this plasma. And then when the matter and proton decouple, then nothing will push it when we push it. The matter will stay at the same place. We don't move anymore. To just evolve with the expansion of the units. So this leaves typical spherical over density in the distribution of galaxies. You can observe today. And this is schematically what it is. So these are the, if you look at the description of galaxies, you can see some patterns, like some bubbles. You don't see the circles exactly like that. Just statistically, if you measure a lot of circles everywhere in the sky, see it. But you have some specific scale that is favor the distribution of galaxies. And this is a standard rule because you can measure the size of this bubble and you can get precise measurement. So there is one measure that is orthogonal to the random side. Okay. That is and then you have one measure that is along the line of sight. This shaped slice of the Lagos. And these two measurements are proportional to the commodic distance at the end. The RD, which is the size of the sun horizon at the end of the drag epoch, so when the matter stops to be pushed by the photons. And then you have also this HRC, so this that gives you the both of them gives you a measurement of the expression history of the universe. These are background evolution of the universe. You are not looking at the nonlinear evolution, but looking at the background expansion of the universe. So, what is a busy survey? It's a multi-object spectroscopy. So the goal is to get the spectra of millions of galaxies in the universe. And to do this, you have first use different surveys, photometric surveys everywhere in the world, the DES survey, of the WISE satellite, to get like a selection of sources that they will then target with a spectroscopic fiber. Okay. Because it's expensive to look at galaxies randomly in the sky. First select the galaxies with a large survey for photometry. Then do some cuts in photometry to select what are the galaxies that they want. And then they look at it with some optic fibers. So they have this telescope, and they have a focal plane. And the very interesting thing about the focal plane is that it's made of I don't know what is the number, but thousands of small robots. And these small robots here, they have some arms and move like this. And there is a small where there is an optic fiber. They can target the galaxy's position in the sky. And this is an improvement compared to the last version. This it was an SDSS, where there was like a plate, it was a metal with some holes that were drilled. Then there was a human operator that was putting optic fiber. So this was taking all day job for this. While here is a robot that can do this very quickly. So they get much faster measurement of the spectroscopy organisms. And then the spectroscopy are sent to this spectrogram. And then you can measure the redshift very precisely of the galaxy. And they get 4 different samples of galaxies. So the first one is a bright galaxy sample. So this is a low redshift sample of galaxy. And they call it bright galaxy because they observe it when the conditions are not great. Sky is not, you cannot go limited. They get a 300,000 shifts. There is a luminous red galaxy, luminous galaxies that are like intermediary redshift band. There are 2 million redshifts like that. Then emission of galaxy, which is a bit further, 2 million for 1,000. And then there is the quasars. Quasars are small distant objects that they have in sample. And what is interesting is that they already have like 6 million redshifts. And it's just the first year of data. They plan to go to 5 years. And it's already twice the number of redshifts of the previous spectroscopic surveys. And then another observable, the fifth observable that they have, is a Lyman upper forest. So here you're not measuring the position of galaxies, but you measure the inside the quasars, you measure the absorption lines in the spectrum. So if you have some gas in the spectrum, you will absorb it, and you have some lines, and the lines are typical tracer of the redshift of the axis. And what they do in practice is that for this prototype being in the middle, they combine the red and the blue together to get just one point. And one step that you need to do to measure precisely the BAO is to do this reconstruction steps. So even if you have a very smooth BAO scale in the beginning, then you have some non-linear evolutionary structure. Okay. Later on, and this will a bit blur your BAO signal, but you have some equations in your scale. So what they do is that you can estimate your density field very approximately, and then do a displacement of your galaxies to go back to where they were before they were impacted by the later Bohr structure. And it gives you a better measurement of the BAO of the scale. And this is what they do. So here's the comparison in gray before construction, and in color is after the construction. And this is a correlation function. So it's the probability to see a galaxy as a function of the distance. And you see there is this peak, around 100 megaparsec. And this peak is the peak of the VAOs, where you have typically more chance to see a galaxy because you are in this. So the goal is that it doesn't change the condition, it will make it more bulky, so you can get a better measurement of position. And this is the full spectrum, so it's a fully transformed of this. So instead of having a peak, you have these oscillations.
So what do they use? The real space or?
So I'm not sure exactly, but I think a combination of both.
A combination.
Depending on which sample is located.
Do you know how they correct for the shift, the DAO, because you have some shift because they only contribution, right?
The shift, I think it's done in this reconstruction step also, no?
There's some shift. Yeah. You know, because they reconstruction is probably just the launch, right? Because it's one, and I think that this shift in the peak, the position of the peak, comes from higher orders there and so on. Okay. So what do they recover?
I think what they state in the paper is that they use the better modeling of the GL compared to previous measurements. So maybe this includes this. And so these are the data they have for the different achievements. So 0.46 in yellow, in red, in blue, etc. And the gray ones are the previous measurements. So in particular for the SDSS measurements. So here is a Cosmo distance very basically to show. Here is a double distance. So this one is orthogonal to the line of sight. This one is below the line of sight. And in the presentation and in the paper, they discuss a lot about this point here. So there's a facing away from the previous measurement of the DSS. They don't know yet why it's so different. But they say it might be just a statistical fluctuation. And then what is interesting is this point here in yellow, that they don't really discuss, they don't say that it's a statistical fluctuation, but this is what drives a big part of the constraints for the energy efficient states. So that is a little about the surface.
So where are the quasars?
And the quasars are not here because here the plot I showed, and this plot is instead of having the distance separated, this one is an average of the two distance on the sphere. And it goes for the quasar and galaxy sample don't have a lot of signal. They only use this plot. While for the other ones, they use two different distances. For this one, they use an average. So for the this green here and the green here, they use the average.
It's like a systematic displacement with respect to the previous, reserve.
Yeah. And so they also did some tests where they took the points of the value of catalog of the DSS and put in their pipeline, because the pipeline is a bit different. And they show that it shifts all the points a little bit down by 0.1 cm. So going down.
Did they test using the SDSS pipeline with the data? Like those.
So the DSS thing also is they have used it, it's more complex because it's a heterogeneous data sets. So different surveys combined with a different data. When they say DAISY is very homogeneous. Then how it translates compared to the here is this average distance to the sphere compared to the blank base fit, which is dash line, and their base fit on the sphere, which is a plain line. So it's like a shifted down with all those components. And then there is a spot here that is very difficult compared to the rest of the words. Here is the Alcon-Paczynski index, so it's a ratio of the orthogonal and the distance.
The dash line is the best fit for W0W.
No, the last line is a blank, oh, sorry.
Which line is it?
The plain line is another CGM.
Okay. So the main difference between the yellow and the red is quite simple. Apparently they are the same sample.
With the yellow and red?
Yes.
It's just the redshift bin. So the same
They
sample.
be in the redshift.
They be in the redshift arbitrarily.
And why?
Because they wanted to have all of the points.
Well, there are different samples, really, the bright gas sample and the LRGs are.
I mean, no,
Sorry, these are, both of them are LRGs, so the bright gas sample is not there. And because it is the one that's that redshift. Around.
So it's very.
Oh, okay, not on the right one.
Yeah. Yeah, because they say. Well, they don't have enough significant to the ratio, so they don't use the average measure, which is this measure, the average distances. When for the other one, you can have a measure of both separately, so because they take the ratio.
So this didn't show like what happens if they use one sample advertisement. Like instead of separating them two, just one.
No, they didn't show that. But one interesting test that they did is to for the spreadsheet points for the redshift bins that are where the survey volume is smaller than the DSS because they didn't finish the survey yet. So for the low points, they have a bigger error bars than in DSS. What they did is they replace points on the DSS points, and then they kept the other one. And they test, they get the same constraints here. So they have to go fast because. So yeah, so when PO measures, so yes, I said because algorithm and this redshift, and then it's a common distance and it's 1250, and so inside it, what you will see is that in practice, what you measure is omega matter and the combination RD times H naught. Okay, so you have omega matter and RD times H naught. And these are the constraints from the different samples of DC. So different colors of different samples, because they get a different redshifts, you have different angles of degeneration. They argue that the RD is consistent with each other. And you can get, combining them, you can get very nice constraints on omega matter times H0 plus. So here it's comparing the SDSS in orange, so the previous to DAISY in blue. And it's a bit shifted to a higher H0 RD and a bit lower omega matter. That was the previous one. by around 1 second. And in pink is the CMB. So it seems that Daisy is shifting a bit to a higher S0. And then, you can break the degeneracy of RD H0 by you can measure H0 if you know RD. RD is given by this thing. So this is the scale of the horizon at the point of the. And you can get it with different ways. One of them is to assume a Big Bang nuclear synthesis theory plus the permanent abundance of the deuterium fracture. So you get omega variance. That's two variance. One of them also is to have the angular sum of the horizon in the CMB observations, or to get a full CMB spectrum to can be great with the synthesis. Then and it is a comparison of the H1 from CMB, which is around 67, and the H1 from Daisy, which is around 68. So it's 1 sigma. But it's still in tension with a direct observation from supernova. It's still 4 seconds.
That's a loop for C.
I think this was it.
No, that's interesting because although people is talking much more about the behavior of the dark energy, for me, the question of the value of it not being different from those who came from large scale structure is very conscious also, maybe for me, more important than the tension regarding
That means there is a tension between the values that you get when you assume on the CDM. Just to get this from the low when you want to assume on the CDM, compared to the one when you don't assume on the CDM. Because here the shows it's directly in your numbers, it's actually. So then they go to measuring the dark energy equation states. So this is the variation of this value of the dark energy. And we see that you can shift the low redshift points by changing the inequalities of the value. And this is when you assume this parameterization, when you have some evolution of the equation of state with a state factor. Here you can also be better the points depending on the value of the value. And this is the measurements they get. So here assuming a constant parameter W, so it's a W omega n plane. It's this blue area of the DZBO compared to the one when you combine with supernovae. So here it's not the same supernovae that we're seeing here. It's not the supernovae that they use. It's just the supernovae that they use to compute the expansion without computing the value of absolute value. You get this area here. And CMB is a big area here. If you combine everything, you get a very nice measurement of -1. So this is a totally compatible with the cosmological positions.
What is like the goal here? I mean, is this really like the true model of dark energy, or they just like pick one and this is really constrained?
So the W is like when you have a tree. So if the energy is not a cosmological constant, it's not lambda. So in the first assumption you can make, it's a tree that can have some negation state. You can assume the homogeneous universe. And then another parameterization that's the way we use is this one, assuming that it's some evolution from big time. And it was shown by some, because it is kind of a very general, and it should encompass a lot of time energy models in sense. But it's debatable.
And then what do you look for? Like, what would you say, okay, this is like dark energy, like you're sure you're seeing and what value W would you want?
So if your W equals -1, you're not advanced. You can have, you don't know if it's a constant, lambda, or if it's a big.
You want W far from 1.
If W is far from -1, then it's something else. But then what they do is that they try to measure this the way. And here, if you only have the VO from Daisy, you have black touch lines, you don't have straights. But if you combine with CMB, you're in the big area. So it's already 2.6 sigma from the initial value of the cosmic substances. And then you can combine also with supernovae. And when you combine everything together, so they get, so there are different supernovae samples. The Pantheon plus, the Onion tree, and the ETS, you get 2.5, 0.5, and 3.9 sigma. And this is where it gets interesting because maybe it's just statistical fluctuation, which is just sigma, or it can be something that is predicted, it's sigma. Interestingly, when they replace the lowest points by the best DSS ones, okay, the points that don't have bigger overs, the bigger overs, but this is replaced by the DSS, they get a bit slighter tension. So you reduce by 0.4 sigma the tension on all these dimensions. And then if you combine with if you want to measure the mass, maybe it's also the most interesting one, because here they get, because they get a high value of H naught. You have in the CMB, you have a degeneracy between neutrino mass and H naught along this line. Okay, so if you get a higher level of H naught, then you get a lower bound to the filaments. Because they get a high H naught, then they get a low bound to the mass, which is of 72 millimolar, which is already below the inverted hierarchy. They conclude that they have 2 sigma preference for the normal hierarchy. But if you go to extension of the CDL, you have less constraints, and if you replace with an SSS point, you have 82 millivolts, which is also below the normal hierarchy, but less tension. Okay, so this was the questions that I had when I made the slides. What drives the higher H naught, the lower median measurement of disease with DSS? Do we get better measurements when we use a full shape or the pure PO? So not only the peak, but everything. Or this will be the future disease like this. Did we see a hint of a dark energy in motion state or situation? Is this a result that is driven by the low redshift supernovae data, or is it the robust stuff? We decrease the tension if we future release of BZ, we get closer to the excess. Will the NSST get a better measurement of that and be able to subtraction? Finally, are we looking at a good parameterization of the NWA? Because there are not super familiar, but you have some part of the theory space that are not very physical. So it might be used.
Thank you for giving 2 talks in the time of 1 and a half. Yes, no.
So, you show that even if you substitute that data as low redshift by a slow data, you still have these. You still have a kind of a weak piece of evolution of dark energy there. It's now in the plots of the actual PAO strings that you have there, it's not so obvious that this is happening there, right? On the basis just of that data. I mean, so you're saying you're keeping the 0.6 data, but the let's say the green and orange and the other orange points are substituted by long data.
Yes, everything is below there. The substituted by this.
Okay. So then the result has to be driven by the high redshift LRGs, not by the other ones, because the other ones are not doing it, right? And they're just consistent with them. Yeah.
Or by CMB, because
well, but then it's not that safe, it's something else, right?
CMB, because the alone it seems okay, but then when you add the CMB, you get shit.
So it has to be driven by this relative, by the high redshift luminous red clouds. That should be coming from the southwest. And that's the conclusion then, right? Because the other points are, if you ignore the other points, you still have basically the same result, given that the high redshift points are obviously consistent with the CDM. It has to be driven by the red ones. No, but if you substitute the yellow by the sloan, then you still have the same result.
Substitute the red also. I think this should be both of them.
Well, that's the question. I mean, it's below redshift 0.6 because the red points are between 0.6 and 0.8. So I'm thinking that the statement is that you still keep the red points, but you ignore the orange one. Because the red points, I mean, if you can go back, the LRGs, they have two parts. There we go. It's between 0.6 and 0.8. So if it's just substituting the below 0.6, you're just substituting the orange ones, not the red. The red one is still there, the red one, which is the high redshift luminous red galaxy.
Yeah, yeah, so it gives,
Yeah.
so.
So it's coming from this.
So it's coming from the red point there.
Has to be.
Yeah.
That's it.
The yellow point doesn't mean much
Yes.
sense in comparison with it.
Exactly. So if the yellow, the orange in this case, whatever, we'll call it is. The yellow, orange point is not doing anything because if you even substitute by slow, which is the gray point there, you still have to, so it has to be.
There was a city this one.
Yeah.
Well, then it's. Right, it's tricky, but sorry, it's so cheating, but
Which kind of galaxies are the points? With minus against.
yeah, it's a targeting color space and they're the same thing, but at the two redshift ranges.
So are they watching the same area for the first station? So how compatible are the regions that they're watching between SCSS and?
Yes, so they are, that they are 70% of our SCSS and the first year.
So I have a question. DASI has this, it will, then it passes, right? Will observe the same region a few times. And it will resample. So in a region, they will observe. I mean, and they can also reassign the fibers. They point to something, they realize it's not what they want. Then they quickly give it away to something else. So the selection is kind of complex. I mean, we were interested in quasars and we were using DASI to check our selection. And we saw that in many cases, you target one thing, and then that ends up being something else. So this was happening around for quasars. I don't know what's happening for red galaxies, but given that the selection that they will reobserve many times, so the final selection is one thing, but the partial selection is something else. And the fact that you reassign fibers. What makes me wonder is, are they sure that there are no systematics from the selection of these objects? Was this discussed in any way at the presentation there?
Yeah, so they were showing a lot of plots. So they did there are two units of simulations for the very then yes, the question, same question, what is your systematic? They say no, we make the land and problem with magnetic variables. So I don't know much more about that. But yeah, because it's interesting that they comment in the talk in the paper about this red point being a statistical fluctuation. And then we will know that if you don't replace this one, but replace the others, then this red point is moving the constraint.
What about neutrinos? Is it the same thing also? Or?
And neutrinos,
How is it dependent on the red or the on some particular?
So neutrinos, I think they also did the same test, but they get a smaller higher bound, right? Here at the bottom. And in my opinion, the neutrinos that is mainly driven by the fact that they get a higher H-naught guarantee measurement. So there is this shifts to the right, lower the upper bound.
So I'm guessing that it's also dependent on the red.
Could be.
Sorry, what?
Thank you.
Yeah, so it's actually the LRGs and the EPS, the ones that are different than the rest. In terms of H-naught and
Okay, but we might you, we have one more talk, and we finish now second the last topic to eat, and then the institute is for hours until No, not midnight, until 6 we can stay. So we have plenty of time after Shank's talk to discuss that. So it's up past noon, I guess we can move to lunch, but not before 10 meters.
Yes, I know, so good afternoon.